Okay, so here we're looking at, the book calls these Newton's second law problems. I'll call them net force and acceleration problems. So in general, we have things that are no longer standing still, things that are no longer in a situation where all their forces are balanced, they're at equilibrium, but things that are experiencing some sort of acceleration. So here are the connections you need to make. F net equals ma. And in physical science, you probably learned F equals ma, and that's true, but it's the net force on the object. Because you can have multiple forces acting on an object. If it's all in equilibrium, if they're all balancing, there's still no acceleration. So it's the net force on the object that's equal to ma. That's not a bad place to start any of these problems. And for all of these problems, the habit that we're slowly starting to build, which really helps you with Part C and Part D in this chapter, is the idea that you've got multiple things that are true that you can describe in multiple ways algebraically. So starting off with F net equals ma is a great place to start. Well then, figuring out where that F net is. Well, how do you figure out F net? Oh, that's a 4a problem. So there you're looking at each axis. And so it's useful always to do a sum of forces on the x and the y. If you only have an unbalanced force, if you only have a net force on one of those axes, hallelujah, because there's your net force, and you know on which axis the motion will be, the acceleration will be. So if we take some example, where sum of forces on the x is 0, so it's not moving laterally, but it has some force on the y, that's when we start with the whole, well, all the forces up minus all the forces down, and then figuring out what those forces up are, what those forces down are. And what we know is that if this is the net force, then this equals this. So really, in all of these equations, in all of these problems, you're starting with two different equations. You're starting with F net equals ma, and you're starting with a sum of forces. And you're getting them both to a point where you can plug them in together, because you're not given enough information with either half of those to solve for anything. All right, so we're going to do number 12. You got cable of an elevator attached to the car and attached to the counterweight. And did you know that this is actually how these things work? So that, elevators, so that you only have to lift the mass of the people in the car and not the mass of the car itself. There's a counterweight, so gravity is doing the work on that, but that's next chapter. Suppose a car with passengers has a mass of 1,600, so mass of car and passengers is 1.600 times 10 to the third kilograms. Mass of the counterweight is 1.200 times 10 to the third kilograms. Calculate the magnitude of the car's net acceleration as it falls from rest at the top of the shaft to the ground 25 meters below. And then calculate final speed. Okay, so what we want to start with, I'm going to shrink this down, just my handy little picture here. We want net acceleration, so we want net force on the car because that's equal to the mass times acceleration. So I'm starting with that. And this is net force on the car, so this is mass of the car with the passengers, not the counterweight. Okay, so I always, on anything from here on out, I always do an F net equals ma, because it'll probably come in handy, and if it doesn't cost you much. Okay, we know that there's no movement on the x-axis. I'm just going to write that as basically I'm writing that as a note to myself that I thought of it, that I accounted for it. I can check it off. It's not something I'm missing. It helps sometimes to do that because especially as you get into problems with more and more variables, it's really good to have sort of a mental checklist. Did I account for this? And especially those of you headed to engineering, did I account for everything? Check, 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 check. Yes, I accounted for that. So I'm going to make a note of that, but I'm not going to have to use it. sum of forces on the y is equal to all the forces up on the car minus all the forces down on the car. And what force up do I have? What do we call the force exerted through a cable? Force of tension. So I know that I have a force of tension up on the car, and I know that the force down is force of gravity on the car with passengers. Now the $64,000 question, what's the force of tension? Oh. Huh? The counterweight, yeah. So where is that force of tension coming from? It's coming from the mass, the force of gravity on the counterweight. So how do we show that algebraically? This is where I would probably put a side note to myself, because I don't, off the top of my head, have a great way to show that. So sum of forces on the y for the counterweight is equal to the force up on that minus force down. And in its case, oh yeah, hey, that's a great way to do it. So force up on the counterweight is force of tension counterweight, and that's going to be equal to the force of gravity on the counterweight. So or would that be force of tension on the car? How to prove that sort of geometrically? How to do this in sort of a proof form? Well, at this point, I'm going to worry a little bit less about that. We'll get it cleaned up later. But what we know is that the force of tension on the car has to equal the force of gravity on the counterweight. Okay, there's nothing else happening there. So that's going to be mass of the counterweight times gravity minus force of gravity on the car with passengers is going to be mass of the car and passengers times gravity. And that whole thing is equal to the net force. Because we know that there's no force on the y-axis, so the net force in this whole system is on the y. Is this helping or muddying? Some combination thereof? Okay. The only way to get good at these is practice. It's painful, it's horrible, but that's just the way it works. Okay. At this point, I'm going to go ahead and do a substitution. So I know that F net is equal to the mass of the car and passengers times acceleration, and F net is also equal to the mass of the counterweight times gravity minus the mass of the car and passengers times gravity. So I'll go ahead and do my magical substitution here. Car and passengers times acceleration equals mass of the counterweight times gravity minus mass of the car and passengers times gravity. Well, what am I solving for? What do I want out of this problem? Go back to the text. Well, before that, there's a preliminary solve. I want the acceleration. I want the acceleration of the car. So, what can I do here? Well, I can't cancel out mass. Why can't I cancel out mass? Looks really tempting. These aren't all the same mass. Two of them are mass of the car and the passenger. One of them is mass of the counterweight. So if I'm solving for acceleration, what do? Well, at this point, the algebra is fairly simple. Now let's see if I actually can get this right. So acceleration is equal to the mass of the counterweight times gravity minus mass of the car and passengers times gravity divided by the mass of the car and passengers. So I'm looking at this. I'm thinking about the dimensional analysis. I feel like there's an issue. Okay, so that was just a brain fart on my part. Dimensional analysis, yeah, it's fine. We're in meters per second. Good, that's what we want. So let's go ahead and plug in values and see if we get the answer that's given by the text. Okay, well, I've managed to foul this one up, and this was not an intentional mistake, so let's see if we can detective work through how this goes. What did I screw up? So the question was, as we try to detective work and find my mistake, did you get it?
No, I got a different answer.
You got a different answer. You got 2.45?
Yeah.
Negative 2.45. That's what I should have gotten using my method. So I'm not sure why we're not getting that. And every now and then the book is wrong, but I'm not going to jump to that because I'm going to assume that I screwed something up. So no, because we're talking about the motion of the car. So that initial F net equals MA is going to be the car and the passengers.
Okay.
So we had a moment where we were talking about the counterweight up here. Whoops. Up here, but that was sort of a different side conversation. So that was a good question to ask, but no. And yeah, I divided by 1200. I wrote down 1600 and then divided by 1200 anyway. So yeah, with this method, I get negative 2.4. We have 3 sig figs. We have 4 sig figs. 2.453 meters per second squared, and that's what you got, Isaac? Okay. Which is wrong, according to the book. So let's track back. What would be the issue with that? We have net force equals mass times acceleration. Is there some force that we're missing over here? So the counterweight gives you force of tension. We're not at a level in physics where we're going to think about, you know, loss of tension over the pulley and any of that. That's way beyond what we're doing. So let me make sure that I didn't copy that wrong. Hold on. Strike number 12. I'm sufficiently ticked off about it. I will figure it out, but for right now, we'll make it a bonus. You show me how you get to that 1.4, I'll give you a bonus point. They have some crazy assumption in there. So that one's overly complicated. Leaving aside the ugly questions that were raised by their set of assumptions, which I'm not going to talk about right now, you know, doing F net equals MA and then doing your sums of forces. Oh, here's one. What if you have a net force on the X and the Y?
4C.
Huh?
4C.
4C. No, 4C is friction. You have problems like this. So if you have an object, here's my object, and it has forces like that, triangle, so you have to find the net force. And in a case like that, it's not going to be cleanly on one axis. Now, can you solve for net force when there are, you know, 5, 6, 10, 20 things pushing on an object, like a roasted turkey? Yes, you can. And once you find it, I'm going to draw this in red. I'm assuming that the net force is somewhere. Okay, this is based on nothing. I'm just making it up. Let's assume that that ends up being your F net here. Can you find MA? Yeah, because now you have the net force. Can you find a heading for the acceleration? Yeah, because whatever heading this is at, you know, if that's 15 degrees north of east. Okay, so your acceleration is, you know, 2.5 meters per second at 15 north of east. Things don't always accelerate on the X or Y axis. So it's just down to, can you find F net? Then can you plug whatever your F net is, can you set that equal to MA? Does that help? You always have to start with those two sort of twin sets of equations. Okay? Now shut up and let you work. I'll put on Pandora.